Hi everyone. For today for 3.5, we're going to learn a couple more theorems about proportional triangles. The first one is called the triangle proportionality theorem, and it's similar to something we did earlier. I said earlier on we did this question where we took a triangle and we drew a line segment through the middle that was parallel to one of its sides, and we said it splits it into two similar triangles, or it creates two similar triangles. The picture looked kind of like this. And here's a new theorem. It says, well, this isn't the new part. This is what we noticed before. We said that top triangle APQ is similar to the whole triangle ACB. But here's the triangle proportionality theorem. It also breaks the sides up into proportional pieces. So it's not the triangle itself. It's a tiny difference here. What it's saying is that, like, this side and this side are proportional to this side and this side. And it's not, see, the bottom pieces aren't the whole side of the big triangle. It's not even really part of the triangle. It's part of the trapezoid. So it's like the two sides here, BP and CQ. And in fact, that's exactly the way I wrote it. I said AP divided by PB, which is that top segment divided by the bottom on the left side, the red arrows, equals AQ divided by QC. So it's a new proportion. What it does is it gives you a slightly easier way to answer the question that we did earlier. And in fact, what I'm going to do for our first example, we're going to repeat the exact same question. So the first time I showed you this question, I gave you the same problem. I gave you this picture, and I said HI is 4 right here. I said LK is 5 down here. IJ is 10 over here. And I asked you to find HL, so we called that our X. Now the way we solved it the first time, we had to add the sides together to find the sides of the big triangle. So you had like an X plus 5 in there, and 4 plus 10 is 14. That part was easy. But having that X plus 5 in there was a little tricky. So what we can do now is we don't have to add that. We can just use the numbers we can see. So we could just say X over 5, that's the ones on the left there, equals 4 over 10. That's the ones on the right. And if we just cross multiply, you have x times 10, that would be 10x, equals 5 times 4, that would be 20. Divide both sides by 10, you end up with x equals 2. Now, that was the same answer we got the first time, but much easier. The last time we did it, we had x over 4 equals x plus 5 over 14. And when you multiplied, you had to use distributive property. You had two different x's. It took several different steps. So what this theorem does, it gives you an easier way to answer that question we did earlier. So whenever you have that picture where you have the perpendicular line going through, I'm sorry, the parallel line going through the middle of a triangle, parallel to any one of the three sides, just remember the two sides that that parallel line breaks up become proportional. Now, let's add to that. So if 3 or more parallel lines are crossed by two transversals, don't get caught up in the vocabulary. You have the 3 parallel lines, you have 2 different lines that are crossing over them. Very simple. The same thing happens. The line segments are proportional. What you're doing is you're kind of taking that same picture and extending it and drawing one more parallel line in there. Because even though it doesn't show in this picture, if I were to extend these lines like this, it kind of makes that triangle picture. Except I just extended it to have 2 parallel lines through the middle instead of 3. But let's take that out. I don't want you to be confused by that. What we're saying here is AB over BC, AB over BC, those two segments are proportional to DE over EF, that side. It's actually the exact same theorem, it's just not a triangle. It's 3 parallel lines and 2 lines. It doesn't actually ever form a triangle, but it's really saying almost the exact same thing. So let's do a new example here. Let's fill in all the information I gave you. AB is 4x minus 7. That goes right here. BC is 6. That goes down here. EF, this one down here on the bottom, is 16, and DE is 24. Let's find AB, which means, first of all, let's solve for x. So let's make fractions. From the left side, I could do 4x minus 7 over 6 equals, and then the same thing on the right, that would be 24 over 16. Now this is a question where what I would probably do, kind of like we did earlier, that 24 over 16 can be reduced, and that makes your work a little easier in the long run. So let's rewrite it as 4x minus 7 over 6 equals, now take the 24 and the 16, reduce it by 8. Divide each of those numbers by 8, and you get 3 over 2. See, now when I'm cross-multiplying, instead of having to distribute a 16 times 4x and 16 times 7, I'm just doing a 2. So I have 2 times 4x minus 7 equals 3 times 6, or 6 times 3. And again, that's 6 times 3 is easier than 6 times 24. So if you can take that fraction and reduce it, you don't have to, but it makes the work a little easier in the long run. Okay, let's see what we get here. 2 times 4x is 8x, minus 2 times 7 is 14, equals 6 times 3 is 18. Solve for x. Let's add 14 to both sides. That was a negative 14 we wanted to cancel. We have 8x equals 32. Divide by 8 to cancel. X ends up equaling 4. So x is 4, but not our answer. The question didn't say solve for x, it said find AB. Well, AB is 4x minus 7. So to finish the question, I want to take that 4x minus 7 and substitute 4 for x. So I have 4 times 4 minus 7. That would be 16 minus 7, and our final answer is 9 for this one. All right, very similar. I mean, I could have given you that exact same question with a triangle and one line going through it, same exact problem. It's just instead of having a triangle, you have the 2 parallel lines, or the 2 lines that might form a triangle, and then 3 parallel lines going through them. Okay, last thing for today, we have a definition, a mid-segment of a triangle. A mid-segment of a triangle, it's kind of what it sounds like. It's a segment that connects midpoints. So if you take any 2 midpoints of a triangle and connect them, if you take any 2 midpoints of sides of a triangle and connect them, that gives you a midsegment. So here's a picture with all 3 of the midsegments drawn in. So I took each side and I split it in half, and you can tell by the markers, like BC has been split exactly in half because you have the one little blue marker there. CD has been split in half because you have the 3 purples, and then on the bottom you have the 2 oranges. So I connected, I found the midpoints, G, F, and E are the 3 midpoints of each segment of the triangle. I connected all of them. I drew in basically all 3 midsegments of a triangle. Now there's a couple important things about midsegments. Number 1, each midsegment is parallel to the other side of the triangle, meaning the one that you didn't use to make it. So like, for example, the bottom of the triangle, BD, is going to be parallel to GF here. And I could have done that for any of the 3 of them. In fact, I'll do one more. CD right here, I'll do 2 arrows, is parallel to GE here, 2 arrows. And then the third one, BC, would be parallel to EF. Number 2, this is the other part of the theorem, or maybe a second theorem. Each midsegment is exactly half the length of the side it's parallel to. And that makes it super easy. If I told you BD, the bottom was 10, then GF is 5. Or if I told you CD, that side over there on the right, was 12, GE is 6. It's exactly half it. So one last example for today. I gave you the same picture we've been working with. I gave you 2 pieces of information. Let's mark our information. So number 1, I told you that angle GEB is 81 degrees. That's this one right here. And BE from here to here, half of the bottom is 10. This is a 10 right here. And I asked you guys to find two things. I asked you to find GF and the measure of angle EFD. So let's take a look at this. The measure of EFD, what we're going to have, you have to look at this very, very carefully. Imagine, I'm going to mark up the picture and then I'll erase it for the second half of the question. Imagine we have this line here, and this line here, which I'm doing bold in red. Those are parallel because that was our first theorem. The midsegment is parallel to the opposite side of it. Now right here, let's focus on this line as a transversal. Now the 81 degrees here is the same as this angle here because those are alternate interior angles from book 1. So the answer to the question, the final answer is 81 degrees. You have to visualize, I marked it really dark in red to show you, but there's all kinds of parallel lines and transversals here. You got to be able to block things out and really just visualize certain things. So what we actually have there is alternate interior angles, which are congruent, and the answer is 81 degrees. Okay, I'm going to take all that stuff out now because I don't want it to confuse us for the rest of the question. The second part is actually easier. I said, what is GF? And we're going to use the fact that BE is 10. Now, to do it the long way, you would say, well, if BE is 10, so is ED. So BD the whole way across is 20. And then our theorem says GF is going to be half that. If BD all the way across is 20, then GF is 20 divided by 10, which is 20 divided by 2, which is 10. Sorry, I got backwards there. 20 divided by 2, and the answer is 10. So the answer is 10 for GF. But another kind of shortcut way of thinking of it, if a midsegment is half of a line segment, and the line segment is split in half, these are always going to be equal. You know, if I tell you that half of a side of a triangle is 10, that's the same as the midsegment. So these were our two answers, 81 degrees and 10. And it all comes down to those midsegment theorems, and a lot of it goes back to the parallel line theorems from book 1. You're going to have to remember those. Whenever there's parallel lines involved, you want to think of corresponding angles, alternate interior angles, etc., etc.